This will be the first lecture on forces and motion. There'll be 3 that pertain to the first portion of the lectures, and then we'll talk more in depth about different forces in later lectures. The goals of this lecture are to learn a little bit about what forces are, especially as they pertain to physics, and then we'll utilize that terminology once we know what forces are to set up Newton's first and second laws of motion. And once we have a pretty good idea of what Newton's first and second laws of motion are all about, we'll go ahead and learn how to create force diagrams, and then we'll utilize those force diagrams and put them together with Newton's second law. So a force is a push or a pull, and we can break forces down into 2 major categories. The first of those categories is long-range forces. Now long-range forces are characterized by forces that can act at a distance. So the main 3 long-range forces that we utilize in physics are gravity. That'll be the most common one we work with, especially in the first semester of physics. And then electrostatic forces. This is a force similar to rubbing a balloon and then holding it above your arm, and you can feel the forces acting on the hairs of your arm. And then if you've played with a magnet, you understand what the magnetic forces are all about and how those can act at a distance. When you bring a magnet close to a metallic object like a refrigerator, you can feel the magnet being pulled towards the refrigerator or pulling the refrigerator towards it. The second category of forces is short-range forces. Now these forces require some sort of physical contact between objects. So a touch is required for a short-range force to take place. So what you need to do is you're looking at diagrams or working with force problems. You have to ask yourself, are there any long-range forces involved? And almost certainly there'll be a gravitational force involved. And then you want to ask yourself, what is touching the object I'm interested in? Because if there's nothing touching it, then only long-range forces can come into play. The other thing you have to understand about forces is forces have to be caused by physical objects. Something must be causing a force, and we'll get into more detail on that later. Now there are 5 main types of forces that we're going to work with for the next several lectures. The first of those is the gravitational force, or what's often referred to as the weight. So keep in mind, weight is a force. It's not a mass. It is very much related to mass, and we'll look at this in more detail later. But weight is equal to mass times the acceleration due to gravity. Weight is a force. The next type of force that we'll work with quite often is a normal force. Now a normal force is always caused by a surface, and the term normal means perpendicular. So a normal force is always perpendicular to the surface, and that's very important. So if you know what the direction of the surface is, the normal force will always be at 90 degrees to that. If you're working with a curved surface, then the normal force is always perpendicular to the tangent to that surface. So if you had some sort of a curved shape like that, then a tangent to that surface at this location would be there, and a normal force would be along this perpendicular. So again, normal means perpendicular. So a normal force is always perpendicular to a surface or to the tangent of the surface. The next type of force we'll come across quite often is a tension. Tensions are generally due to strings, possibly springs, maybe a cable or a rope. Something like that will generally cause a tension. Now related to tension and oftentimes lumped in with tensions are compressions. I've separated the 2 here because a rope or a string cannot exert a compression. But if you think about a wagon that you might have played with when you were a kid, there was a handle on that wagon, generally made of steel. And you could pull on that handle. And when you did, you were exerting a tension on the wagon. But you could also push the wagon backwards by pushing on the handle. Now that's going to take a solid, inflexible object. So a cable can't do that generally. Maybe at small distances it can. But a rope or string will not involve a compression. They'll only involve a pull or a tension. So a push or compression can only be exerted by a solid, inflexible object. And then finally we have friction. Friction is another surface force, but in this case that surface force is always along the surface. So this would be parallel to the surface. Frictional forces are fairly complicated. We'll discuss them a little bit in this lecture, but for the most part there'll be several lectures down the road. One thing I will mention about friction is that it is always opposed to a sliding or an intended sliding. So you want to look at what direction something is sliding or wants to slide, and that will give you an idea of what direction friction is. Again, we'll talk about friction over the next few lectures, but we'll get into it in more detail much later on. So here's the first of Newton's laws. Newton's first law says, and some of you may have heard this already before, but Newton's first law says a body in motion will stay in motion, and that includes moving with a constant speed and in a straight line, unless it's acted on by an outside net force. And this whole term net force and outside force will be very important. We'll get into outside force more later on, but net force we'll be talking about here during this lecture. So if an object is at rest, that means it has a speed of 0 and it's going to stay that way. So you'll also hear an object at rest will remain at rest as another portion of Newton's first law. But that's really all written in here. So at body at rest just moves with a constant speed of 0, or doesn't move with a constant speed of 0. But this concept of the straight line is also important. If you change direction, then Newton's law states that you must have some net outside force acting on you in order to change direction. Now, some really good examples of this would include if you're driving down the road and you have, say, a cup of coffee on your dash. If you stop the car suddenly, the cup of coffee spills. Now, the reason for that is that the cup of coffee is a body in motion. It wants to remain in motion, moving forward with your automobile. But when you hit the brakes, an outside force, and that force is actually the road, an outside force stops your car. But that outside force isn't acting on the cup of coffee. And the only force acting on the cup of coffee is the surface force of your dashboard, and that's insufficient to stop the cup of coffee from moving forward. And so it spills in the forward direction. The same thing would occur if you make a turn in your automobile. When you turn left or right, if you have a cup of coffee on your dashboard, it might spill over because there's not enough force pushing it to the left or the right, whichever direction you're turning, in order to cause that cup of coffee to make the turn. And so it continues trying to move down the road, whereas the rest of your car is moving left or right. Now I should point out that the road is what causes your car to turn left or right, or what causes your car to start or stop. It isn't the brakes, it isn't the motor, it isn't the steering wheel. It's the road. And the way you know that is by doing a little thought experiment. If you consider your car to be moving down the road on a perfectly frictionless surface of road, the road is covered with perfect ice, you can turn the wheel. You'll continue to move down the road, not move left, not move right. You're going to continue straight down the road. You're going to move with a constant speed. If you hit the gas, the engine revs and your tires turn, but you can't go any faster. Your tires will just spin against that perfect ice. And then if you try to stop your car, the brakes are functioning, the tires stop rotating, but you don't slow down. Because the ice is perfectly frictionless, you don't slow down, you don't speed up, you don't turn left, you don't turn right. So all of the things you think would stop your car, your brakes, start your car, your motor, turn your car, your steering wheel, all of those are working fine on a frictionless surface. And yet you don't stop, you don't start, and you don't turn. It's the outside force, outside of your car, that is the road, that causes you to stop, start, turn left, or turn right. So it must be outside your system. Another example of trying to do something internal, try lifting yourself up by your bootstrings. In other words, grab your feet and lift, and you can't lift yourself up. That's internal to your system. In order for you to get off the ground, something external to you must lift you off the ground. When you jump off the ground, it isn't your legs that propel you off the ground. It's the floor that propels you off the ground. And in fact, that's a normal force. That's what makes you jump. And your legs do have something to do with it. We'll talk about that when we talk about Newton's third law, which is in another lecture. Another thing to keep in mind is that all of Newton's laws are only valid in an inertial reference frame. An inertial reference frame is a non-accelerating reference frame. We've talked about acceleration already. But a reference frame that is not accelerating is referred to as an inertial reference frame. Now, a good example of a non-inertial reference frame is a boxcar. So imagine, if you will, you're inside of a boxcar, and on the floor of the boxcar is a hockey puck. And we'll assume the boxcar has a very frictionless surface as well. So if you're inside the boxcar and it's a perfectly smooth ride, you don't know if you're moving or not. So the hockey puck is in the middle of the floor, not going anywhere. But if the boxcar is moving, and it's moving with a constant velocity, nothing's going to change inside of the boxcar. But if the boxcar begins to accelerate, so another car is pushing it or pulling it and making it speed up or slow down, if that happens, then the boxcar, let's say, speeds up, but the hockey puck will continue to move with the velocity it had before the boxcar sped up. So if the boxcar speeds up, moving faster in the forward direction, inside of the boxcar, we're going to see the puck move backward. Now, as we examine the puck, there are no forces acting on it towards the front or towards the back of the boxcar. And yet it's moving, starting at rest, and now moving in the backward direction. And so that breaks Newton's first law. It's not staying with a speed of 0, it's changing speed, and yet there are no forces acting on it. And that's what I mean by Newton's first law being broken in this non-inertial, that is to say, accelerating reference frame. The other thing you might do is have the boxcar turn a corner. Let's say the boxcar is turning to the left. The hockey puck will begin to move to the right as we view it in the boxcar. And yet there are no forces acting on the hockey puck to the right. And so Newton's first law is apparently broken in that scenario. And that's because the boxcar, because it's an accelerating reference frame, is not an inertial reference frame. Same thing holds true with Newton's second law. It has to be an inertial reference frame. And for the most part in this course, we'll just continue to talk about inertial reference frames without even using that terminology. I want to remind you that acceleration is not velocity. They are both vector quantities, but acceleration is, by definition, the derivative of velocity with respect to time. Okay, so I can write it out as an equation. Acceleration is the derivative of velocity with respect to time. That is to say, the change in velocity with respect to time. Now, as we look at Newton's second law, I want you to notice the summation signs. And what this is also referred to oftentimes is superposition. And the idea here is that if there are multiple forces acting on an object, then I need to look at all of those forces acting together, that is to say, added together. That's going to be the sum of forces. That's going to be what we call the net force. And as we study Newton's second law, keep in mind that these are vector quantities. And so you're going to want to set up some sort of an axis when we're talking about these problems and drawing out diagrams. You need to know where's your x-axis, where's your y-axis, and on occasion, where's your z-axis. So Newton's second law is most easily stated in the form of an equation right there. The net force, notice vector quantities, do not ignore that, equals mass times acceleration, also a vector quantity. Do not ignore the vector concept here. So the net force, that means the sum of all of the forces acting on the object, equals the mass of the object times the acceleration of the object. And in general, I'm going to look at the forces in the x direction and the forces in the y direction. And we'll look at writing out these equations at a later time. So the units for force are going to be found by looking at the units for mass, which in the metric system is kilograms, times the units for acceleration, which is meters per second squared. So the units for force are in fact kilograms, meters per second squared, and we refer to that as the Newton, and we'll use the capital letter N for the Newton. So that is the unit of force in the metric system. In the English system, the unit of mass is the slug, and the unit of acceleration is feet per second squared, and that's referred to as the pound. Well, a freely falling object has an acceleration due to gravity, and so the mass of an object times the acceleration due to gravity, and the acceleration due to gravity exists even if the object is not falling, and so mass times the acceleration due to gravity is a very specific force. It's the force due to gravity, and this is what we refer to as weight, as I stated earlier. So the weight of an object is a force, and it's equal to the mass of the object times the acceleration due to gravity at whatever location the object is at. So your weight on the moon is less. Your mass is not any different, but your weight on the moon is less. So if you weighed 180 pounds on the Earth, where the acceleration due to gravity is about 10 meters per second squared, on the moon, the acceleration due to gravity is 1/6 of that, or about 1.6 meters per second squared. And so your weight on the moon would only be 30 pounds. but your mass would be the same in either scenario. So pounds is a unit of weight, generally associated with the English system, and newtons is a unit of weight. That's the one we'll be using almost all of the time in these lectures, and that is in the metric system.